But actually, trouble with
Right. Oh, okay.
No, I did it most of it.
What's up, dude? Thanks. Oh, man.
Yeah, you'll be happy to say.
Okay, in the interest of not wasting anyone else's time, let's get started. So, as a foreigner that's here taking a British person's job, it's a real honor to give the first post-Brexit one of these seminars. Yeah. So the upshot of what I'd like to, the broad idea of what I'd like to talk about today, is that this program that's going on at the Newton Institute over the next few weeks has a lot to do with scattering amplitudes and myriad advances that we've made in the study of these objects in gauge theory and gravity and other quantum field theories. And the basic question I'm trying to ask this morning is, can we make similar advances in the analogs of scattering amplitudes on spacetimes that aren't asymptotically flat or aren't Minkowski space? Okay? So it's sort of a simple question, and it might seem like an esoteric question because the effects of gravity are very weak compared to everything else, but of course it's an important point of principle, at least theoretically, because we're not living in a space-time that has a vanishing cosmological constant, or so it appears. Okay, so anyway, so just to get us all on the same page, what are the sorts of observables that I'm going to be talking about? So in an asymptotically flat spacetime, the thing that I want you to keep in mind is the S matrix, or scattering amplitudes. Okay, and these are just so I have my conformally compactified picture here. I have Scri plus, Scri minus. I have some incoming states, which I can think of as non-interacting wave packets, say of positive frequency at Scri minus. I evolve them through the spacetime using the Lagrangian or Feynman rules. And I propagate them out to Scri plus, where I have some outgoing states. So I feel like I have some in here, some out there. So external states. These are things like plane waves with frequency conditions asymptotically at Scri plus minus. And the evolution problem is operationalized traditionally with Feynman rules. Okay, so in the case of Minkowski space, this is what I think pretty much everyone will be talking about when they give a scattering amplitudes talk for the remainder of this program. Certainly the thing we kind of learn to compute in graduate school. But now, what about, say, asymptotically anti-de Sitter space? So there's no S matrix anymore in an asymptotically anti-de Sitter space. Instead, what I have are boundary correlation functions or, if you like, transition amplitudes. And so now the picture is this one, and I specify some boundary values for whatever my field is. And then I propagate through the bulk, again using the space-time action. So here I have some boundary of ADS, here I have the bulk. And
by ADS, do you mean hyperbolic space here?
I mean, if you want to think Euclidean, you can think Euclidean. So one moral of the story is that there's some sense in which asymptotically ADS and asymptotically, so Euclidean asymptotically ADS and Lorentzian asymptotically de Sitter are like analytic continuations of each other. So if you're more comfortable just thinking of these as sort of two sides of the same coin, then that's fine. But no, here I could also mean just Lorentzian ADS. So, but the point is that somehow hyperbolicity means that the evolution problem is uniquely governed up to regularity conditions by specifying boundary values for the fields. So if you like here the problem is external states. These are just specified by boundary values. For linearized solutions. Which propagate on the nonlinear asymptotically anti-de Sitter background. And the evolution or computational problem is in the bulk, you could the lingua would be Witten diagrams, or you could invoke ADS CFT and say you're just computing some CFT correlator in the boundary.
Let me repeat my question. I'm happy with everything you said if it's hyperbolic space, but in Lorentzian signature, it's more non-trivial, right? There's also some initial data that need to be specified, so it's more involved story.
Well, okay, so there's no good. So the boundary is time-like. If I'm in the Lorentzian setting, so if you like, let's just consider Euclidean to make you happier for the time being. Okay. So now the third case, asymptotically de Sitter, or if you like, the cosmologically relevant case. So now there is a at least mathematically, a mathematically well-defined notion of S matrix in an asymptotically de Sitter space-time, but no physical observer can measure it. Okay, so I'm not going to talk about that today, and instead, what you should have in mind are what I'll refer to as in correlation functions. And here the idea is that I take, say, the Poincare patch of de Sitter space. So here's my asymptotic scribe plus some sphere, and here's the horizon. And I specify some operators located at the future, and I evolve them through the bulk and back out to the future. So if you like the kind of picture you have is you pick some vacuum, usually taken to be the Bunch-Davies vacuum, for instance. And then you have some operators which you evolve using the interacting Hamiltonian. So they're at some constant conformal time slice, say. And then you take the limit as that conformal time slice runs out to the boundary. So then just to draw a picture, you might have your constant conformal time slice here with your favorite operators sitting on it. And then you take the limit as it goes to 0. Okay. And so this is the region that you're integrating over. So you're not doing a global calculation on de Sitter space, but you're doing a calculation on the observable patch of an observer in de Sitter space. So here are the external states. Again, you now have some linearized solutions with prescribed fall-off conditions at very late times and very early times, so at the horizon and at the conformal boundary. So And then usually you also have to have some choice of integration contour, which is something I can talk more about if you want to hear more about it. But this boils down to some sort of Hartle-Hawking prescription. Let's see. What I mean by that is that you want the linearized fields to die off to zero near the horizon, basically. And to do this, it means you're doing some conformal time integral, and you have to tip this conformal time integral slightly into the imaginary. The evolution problem, this is operationalized by the interacting Hamiltonian on the background. Okay, so these are the three different classes of observables I want to talk about today. But let's really quickly just recap what do we know about these kind of observables. So from now on, just to make things completely concrete, I'm just going to be talking about the semi-classical or tree-level versions of these observables, and the backgrounds will just be the maximally symmetric ones. So Minkowski space, pure ADS, pure DS. Okay? So what do we know? So in the Minkowski space case, we know everything. Okay? So yesterday, Lionel told us about some very nice formulae in ambi-twistor space that captured the entire tree-level S matrices of gauge theory, gravity, and many other massless quantum field theories in Minkowski space. So we know everything about this, if you like, perturbative evolution problem in Minkowski space. Okay? But in the ADS and the DS cases, by comparison, we know almost nothing. Okay? So we know 3 points, and depending on who you talk to, 4 points functions. And when I say depending on who you talk to, I mean that these 4-point functions are known in some very non-elegant versions. So you have some expression that looks like it fits on a line, but it's defined in terms of some symbols, which themselves are defined in terms of an expression that takes up 2 lines, and so on and so forth.
So the Raju BCF formally,
That's exactly what I'm talking about.
Okay. I thought they went beyond 4 points, but.
Are you talking about the current commutators, the current correlators, or the gauge theory correlators?
So I'm talking about, so in the ABS case, what I'm talking about would be equivalent to a correlation function of current in a CFT of 1 dimension lower. So at 3 points, these things are completely fixed by conformal symmetry in both the DS and ADS case, because there's just some sort of quick rotation between the two. And yes, there's some sort of recursive definition of this 4-point guy, or if you like, a definition that kind of bootstraps using OPEs, but it's not a pretty definition. It doesn't fit on one line or anything. Whereas these all fit on one line in some sense. Okay.
Do you have a specific theory in bulk in mind? Or
So I'm just thinking about classical, some classical field theory coupled to the metric. So scalars, gauge fields, gravitons, things like this. Okay.
They're slightly different objects. In the first case, they're the gluon tree amplitudes. In the second case, they're the current.
Okay, no, but so okay, let's fix whether we're going to talk from a boundary perspective or bulk.
Okay.
Talking from a bulk perspective, what I'm talking about are the analogs of gluon scattering amplitudes on a background with cosmological constant. So I'm considering, if you like, the well here. Let me make a very definite statement. These objects have many similarities. First of all, the computations that I'm talking about here, all that it boils down to is extracting the multilinear piece of whatever the classical action of the theory that you want to study is. So in this case, I'm considering the Yang-Mills action on a de Sitter background. Let me take the de Sitter background to be non-dynamical, it's just something fixed. And I just want to extract the trilinear piece of that action, evaluated on linearized solutions to the Yang-Mills equations. Okay? So it really is like a scattering amplitude. The difference is the boundary structure. Is that clear? Now, by ADS CFT, that has to be equal to a 3-point function of some currents. But that's just a symmetry argument. Right now, you could forget about ADS CFT if you wanted to. And I'm just thinking from the bulk perspective, I just want to know what are the natural perturbative observables in ADS or DS. Okay? They're not S matrix elements, but they're something like an S matrix. So but in all three of these cases, the calculation always looks like extracting the multilinear part of some action function. And this is what I mean by extracting the multilinear piece. Okay.
But in practice, is this the way to do the calculation, or you think in terms of doing Feynman diagrams?
Right, exactly. So you can think about the scattering amplitude in this way. This is a complicated combinatorial and variational problem, which we traditionally operationalize using Feynman diagrams. Okay? But at the end of the day, that's what in all three cases, it boils down to something like this. And the difference between the three cases comes into what you mean by these linearized perturbations. Okay? Is that totally clear to everyone?
So you're going to compute in position space?
Right, okay, so I have some choice, and it turns out that there are well-defined notions of momentum space in all three of these cases. But not for, let's say I wanted to be in D equal 4. Here I have 4 momentum, and in these two cases I only have 3 momentum. Okay?
You're putting on shell the external legs.
Yeah.
The notion of on shell.
Yeah, absolutely. So the external states are always solutions to the linearized equations of motion. Okay. So again, if you want to think in the ADS CFT context, think these external states are like bulk to boundary propagators. Right? They're solutions to the equations of motion with some specified fall-off behavior as you run away to infinity. Okay? Or if you like in the ADS case, they're the analogs of plane waves that preserve the Bunch-Davies vacuum go to a constant at scribe plus and go to 0 as you approach the horizon. And that's something unique once you specify that you're in the Bunch-Davies vacuum. So, okay, all three of these calculations look like extracting some multilinear piece of an action functional. There's also a diagram by diagram correspondence in all three cases. And I have in mind something very precise here, so I'll put it in parentheses. I mean the correspondence that's provided by something called the Mellin transform. So if you take a Witten diagram and you perform some integral transform of it called a Mellin transform, it becomes something that looks very much like a Feynman diagram. And you can do this diagram by diagram in the Witten diagram expansion of some ADS correlation function. And by doing this transform, you can make it look, diagram by diagram, this other set of variables, these Mellin variables, like a Feynman diagram expansion. Okay? Also, in DS and ADS, these correlators obey factorization relations that are akin, I mean, if this means something to you, then you'll know what I mean, that are akin to something called BCFW recursion for scattering amplitudes. Okay? And then also there's tons of nice little tricks that we often use when we're working with scattering amplitudes in special dimensions, say 4 dimensions, say like spinor helicity formalism. or twistor variables. That also apply equally well to all three of these settings. Okay, so
This is not clear because we often use spin-helicity for momentum. Right? For
That's right.
momentum, as you said, you only have the three.
That's right. So again, here I have something very precise in mind. So I sort of doubt that these are the guys who came up with it, but there is a notion of spinor helicity for three momentum when you're in DS or Euclidean ADS4. And what you do is instead of having an SL2 cross SL2, you have the diagonal SL2 inside the de Sitter group. So you have some SO3. And then you can use that. So instead of a dotted and an undotted spinor representation, you now just have two undotted spinor representations. And you can use that to build three momentum. And then from that construct an on-shell four momentum just by making the fourth component equal to the norm. And twistor variables somehow obviously work in all three settings because twistor space is some conformally invariant notion, and these guys are all conformally equivalent. So my point here is not that you should understand precisely what I mean by all these points. My point is just like, in broad particulars, these three calculations are the same. Okay? And yet, there seems to be an enormous gulf between what we know for scattering amplitudes and what we know for these other observables. Okay?
The 3-point amplitude in the ADS case, the 3 gluon amplitude, just at tree level, just differs from the flat space case by replacing the Minkowski metric with the ADS metric.
That's right. It also differs in boundary conditions, though. So you can't take a smooth flat space limit of the 3-point function here and arrive at the 3-point vertex for Yang-Mills theory in Minkowski space. And that's not because of something that's happening in the action. It's because of what's happening with what you mean by the external states here.
We usually write the 3-point amplitude in terms of 4 momenta. Right? I think we usually write the 3-point amplitude in terms of 4 momenta, null 4 momenta of particles being scattered in Minkowski space. Right? But this is absent.
Yeah, so maybe a really...
If you were in position space and you computed the 3 gluon amplitude in Minkowski space, and then you did it for the ADS case, you would see they're exactly equal except that the Adamo unit is replaced by the G unit of the ADS.
Okay, so let's take a very specific example, 4 dimensions. Right? So Yang-Mills theory in 4 dimensions is conformally invariant, so the action doesn't know whether it's on de Sitter space or anti-de Sitter space. Right? The way it knows is in these boundary conditions. So let's consider, sorry, this is a brief detour for everyone else, but perhaps it will be illuminating. So let me consider the MHV, right? So let me consider the 3-point MHV amplitude in Minkowski space, right? This is just the Park-Taylor formula. And I would write it, I have some 4 momentum conserving delta function. And then I would have, say, 1, 2, 3, 2, 3, 3, 1. Okay. All right? Now, in ADS, Euclidean ADS or de Sitter, what I would have here is a 3 momentum conserving delta function. I'd have the same spinor helicity, guys. And then I would have a pole in the total energy of the correlation function. There's also some crap here that preserves a Ward identity, but I'm not going to write it down for now. This pole in energy is what turns this 3 momentum conserving delta function into a 4 momentum conserving delta function in the flat space limit. The reason why it's a pole here and not a delta function is because of this contour integral prescription you had to take to make this consistent with the Bunch-Davies vacuum. Okay? So if I cover up all this stuff, they do look exactly the same. This bit is generated just by the contractions of polarization tensors and derivatives in the action. The action doesn't change because it's conformally invariant. But the integral you do changes because the boundary is different. Okay? And that's why they're not equal. Okay?
When it's the integration you make, you have an integral over R in time. They say you've got an integral over R plus.
That's right. Okay? So they're different in a very precise way. And the difference is entirely captured by the boundary structure. Okay?
Yeah, I just had a question. So in flat space, you have an LSZ prescription,
Mhm.
adds you out some stuff, but in the ADS and DS cases?
No, so if
Yeah,
you
so-
like, that's part of what I mean by the boundary conditions on what you're talking about here. So if you like, one way of viewing the asymptotically flat case, you compute a correlation function.
Yeah.
You pull the operator insertions out to scry minus and scry plus and amputate.
Yeah.
It takes some pull.
And that's important though, right? Because it makes it independent of like the variables you chose.
Absolutely, absolutely. So I mean, crucially, these kind of observables
Yeah.
are not actually gauge invariant in
Right,
the sense that something here is because I'm not integrating over the whole space.
Okay. That's one thing that doesn't
Yeah, yeah,
carry through. Okay.
Yeah, exactly. But again, it's not being carried through precisely because of the boundary, the boundary behavior. Okay. So yeah,
You're also going to talk about the all minus and all plus amplitudes?
I will say something about them. That's right. Yeah. For now, let me treat that as a technical aside, which will be dealt with in due course.
If you didn't write them in spinor helicity notation, you wrote them with the polarization
Mhm.
vectors, then I think that you would see that it's exactly the same expression except the metric is.
No.
What is the state represented by the polarization vector
The what?
on the gauge theory side?
The point is not the polarization vectors. The point is the integral domain. That's it.
I mean, it's a delta function though. You change
Yeah.
the four-dimensional momentum conserving delta function becomes three-dimensional
Momentum space.
times
Position
divided by energy.
space.
But if you're in position space, the bit that is kind of going up, you take the cubic part of the action, so it'd be a
That's
squared
right,
dA,
you just see that you.
but you'd insert into those A's different things in the flat space case.
Yeah.
In the flat space case, you'd insert plane waves. In the ADS case, you'd insert delta boundary properties. They're different.
But I think I agree because at the end of the calculation you would amputate the propagators. And so I think I agree with Greece that in position space it's the same amplitude, no matter whether it doesn't matter where
The
you
integrand will be the same in position space. I'll give you that much. But then you have to integrate and
Over what?
I mean, there's more information there. The residue of the pole in E is precisely the amplitude in some sense.
In
Yeah.
in momentum space.
Yeah, in momentum space.
So I wasn't talking about momentum space.
Yeah, okay, so in position space, you're integrating over half of conformity compacted by the Minkowski space instead of all of it. And
You're
that's what the
integrating
distinction
over-
is.
I'm sorry, you're integrating over what?
You're integrating over half of conformity compacted by the Minkowski space instead of all of it.
So actually, I'm a little bit confused about the difference between the sitter and ADS.
Okay, so here in the de Sitter case, I'm just integrating over the Poincare patch. So that's equivalent to the Euclidean ADS calculation because those coordinates are global in Euclidean ADS.
But it's not conformally equivalent to global Minkowski.
Yes, correct.
I think in position space the 3 point is just the trivalent part of the Lagrangian.
Yeah.
And because the Lagrangian doesn't change. So in position space amplitude doesn't change. It's true.
But the domain changes.
What's that?
The domain.
Yeah, but yeah, okay. I mean, we're just banging our heads against the wall here because I'm just going to keep saying the same thing. You can read off the cubic part of the Lagrangian, and they will be the same.
I'm not disagreeing with your
Okay.
formulas, I'm just making a comment.
Okay, but what I'm saying is that if you wanted to extract an amplitude or something like an amplitude there, you don't just give me the cubic part of the Lagrangian. You put in linearized solutions to the equations of motion, three of them, three different ones into that cubic Lagrangian. And those have to solve a PDE with some boundary conditions. The boundary conditions are different,
Yes.
okay? Okay, so the basic question is, there's all this stuff about these things that are the same, and yet we know almost nothing about the kind of classes with cosmological constant, and we seem to know everything about the class with no cosmological constant. So what's going on, right? And today, in the remaining time, I'd just like to outline one possible approach to trying to make some more progress on these non-asymptotically flat cases that uses something called twistor theory. Okay. All right. So the idea, basic idea. We want to divide the computation into two parts. Some boundary part and some bulk part. Now, what do I mean by this? By the boundary part, I mean precisely what we were just discussing. The nature of the linearized external states that you plug into your computation and the contour of integration that you take, say, if you were in momentum space. So this depends on the sign of the cosmological constant set. Okay? This bulk part governs the evolution problem once you pick these external states. Okay? And this is universal. It's just governed by the action. Someone's not happy? Yeah.
I can imagine some theories where there are further couplings to scalars to some space-time curvature that you don't have in the flat space case, right? There are new vertices in the action proportion.
Yeah, no. My claim is not that the action doesn't change. The action is a smooth function of the curvature. Right? These boundary conditions are not. They jump around when the sign of lambda changes. Okay? I mean, if nothing changed, then there wouldn't be a talk to give. Okay. So clearly, traditional methods aren't able to perform this split cleanly, or else we would have made as much progress in ADS or DS as we have in Minkowski space. But the idea is that using twistor variables, you can get this split cleanly in the special case of D equals 4 gauge theory and gravity. Okay? And my claim is that by using these twistor variables, one can write down something that captures everything about the bulk dynamics that goes into the computation of one of these things. And it's universal, endpoints, captures all the tree-level bulk dynamics, and the only thing it's not getting are these boundary conditions. Okay? So it doesn't solve the problem, but it makes much more progress than what the current state of play is. Okay? And the way it does this is using a language of integral kernels. Okay. So what do I mean by all of this? So let's review the state of play in Minkowski space. So scattering amplitudes. So remember, I'm going to be in 4 dimensions for the rest of this talk. Okay, so I'm going to write a formula on the board, and then I'll explain what I've written. So it probably won't make sense to you. Okay, so what have I written here? I've written some integral formula. This piece here is an integral over the space of maps, out of sigma, from a Riemann surface, genus 0 closed Riemann surface, to an open subset of complex projective 3 space with n fermionic directions. So just think of CP3, complex projective 3 space, and then I have some algebraic anti-commuting directions that I've added to this, n of them. Okay? And so such a map I can think of as a polynomial with some coefficients ZR, and then in homogeneous coordinates on the Riemann sphere, say sigma 1 and sigma 2, can always be written in this way. And so this measure is just over the coefficients of this map. So the moduli of the degree D map, if you like. Okay? And I have some integrand. And this guy carries some form weight on copies of the Riemann surface. So this dude is, I guess he's a section of n copies of the canonical bundle. Okay. So he's a holomorphic one form in n copies of this worldsheet sigma. And these dudes are some distributional delta functions with form weight. So they're like 0, 3 forms. And all that they're doing is enforcing the projective equivalence of the point that this map, so there's some point on the Riemann surface, sigma I, and it gets mapped to a point in this complex projective space. All this delta function is saying is that the target of that map is fixed to be equal to, up to projective rescalings, some fixed point in the target space, Zi. Okay? So they enforce so for the twister enthusiasts in the crowd, probably this is all old hat, but for everyone else, just don't worry too much about what these symbols mean. I just have some measure, right? It's like a measure of zero modes of some map, in the context of string theory, perhaps. I have some integrand that carries some form weight, and then I have some delta functions, okay? And because of the form degree carried by this integrand, this whole object is itself a form, if you like, on n different copies of the twistor space. It's a 2 form. And it will have some weight depending on what n is, big N is. But that's not necessarily important. Okay? So I've written some formula. If I did all these integrals, I would get some distributional form on n different copies of what I'm calling PT. So n different copies of the complex projective space, if you like, or some open subset thereof. All right? And the claim is that for n equal 4, this is going to encode all tree-level amplitudes of n equal 4 super Yang-Mills theory. And for n equal 8, this encodes all tree-level amplitudes of n equal 8 supergravity for appropriately chosen I. Okay. And these two formulae have names, although there's perhaps no reason that everyone in the room should know those names off the top of their head.
So Tim, what's PT again? It's some open subset, but what's it mean?
It's twistor space, basically. So the reason why it's open has to do with the existence of certain cohomologies, or if you like, the fact that you're not working on a conformally compactified spacetime. But let me dodge the technicalities of that. PT just means an open subset of this complex projective space at the time. But if it's easier to just think of the complex projective space, then by all means just do so.
In ADS, what's PT?
In ADS, PT is CP, an open subset of CP3/n equipped with a certain contact structure that's non-degenerate.
What's the open subset?
The open subset is the subset on which, so I remove a hypersurface, I guess. I want to consider all rational curves in the subspace given by XAB such that X dot I, where I defines the contact structure, is non-zero.
I mean, I reckon you can probably still do it with a.
But it's a complex hypersurface you remove.
Yeah, it's no longer a line. I mean,
No, you don't want to do that. Otherwise it's Stein. But I mean, what you probably want is a thickening of the end.
Well, but you told me these are maps to PT. I don't think you're going to find them.
No, you will in a thickening of the end.
Appropriate degree?
Yeah, because you can get degree D with D lines and Minkowski space, and you then merge them together, they'll still be close to PN. Hopefully you can get a whole contour in there. I don't know how to do it, but it's
There's
not.
also a contour, an integration cycle on that.
Yeah.
Yeah, so you have to be able to get a contour that's somehow close to D copies of Minkowski space. But I think you could probably do it.
I think you can probably do it as well, but I think a lot of the subtleties of whether this formula is really true in ADS, DS, etc.
Okay, I haven't written a formula in
I
ADS
don't think it's
and
any
DS.
worse than Minkowski.
I agree. I agree.
So yeah.
For the other civilians, this is a Minkowski space formula. Okay? Alright, so the integrands that I have in mind, so for n equal 4,
is not right. Minkowski.
I take this I, N, D. This is just some product. Some cyclic product of the positions of these marked points, sigma I, on this CP1, sigma. And this is something called the RSVW formula. And for n equal 8 supergravity, this is something a little bit more complicated. It's given by the determinants of some matrices. Okay? These matrices somehow know that you're in Minkowski space in a way that I'm not going to say for the time being. Okay? But the point is that these integrands are relatively compact things. You can read off what the entries of these matrices are. This is called the Kachaze schema formula. Okay, but as written, this object is not a function of positions or momenta, right? It's just some distributional form on twistor space with certain weights. And I'm claiming that it encodes tree-level S matrices. So how is that true? Well, you get S matrix elements by pairing with external wave functions. What I mean by this explicitly is that you would write an actual amplitude, so an n point, n to the d minus 1 MHV amplitude. So this is in n to the d minus 1 MHV tree level. If you don't know what that means, this is just some helicity decomposition of all the tree level amplitudes of gauge theory and gravity in 4 dimensions. You get this by pairing this integral kernel against some integrals over copies of this twistor space with some choices of external wave functions of this twistor space. So these external wave functions are some cohomology data. And there's something called the Penrose transform that tells you can represent things like all linearized solutions to the field equations by dudes living in this space. Okay? So again, being completely hand-wavy, for instance, you can take AI to correspond to plane waves, and then doing all these integrals will give you a momentum space amplitude expression, okay? Which you can check is correct. All right? However, this language seems to be doing exactly what we were looking for. I have some integral kernel, which seems to capture everything about the bulk propagation of the fields, and then the boundary data is specified completely by some choice of contour and the choice of these external states that you plug in. So the take-home message here is that in Minkowski space, this twistor language seems to provide a clean split between the bulk and the boundary parts of the computational problem. I know I'm not providing you with any details for the sake of time and perhaps your sanity, But I'm asking you to believe me that this is indeed the case. Okay? So now the idea is to try and generalize these integral kernels to the case when lambda is not equal to 0. Okay? And the hope is that they should then capture everything about the bulk computational problem in those more general settings. All right? Now, when I say generalize them to the case when lambda is not equal to 0, what sort of properties should the right answer have? Okay? I don't want to just write anything down. So it turns out that there are a few things you can hang your hat on to make sure that you're not doing something completely stupid. So what properties should an integral kernel, we just call it m tilde, have for lambda not equal to 0? Okay? Well, it should have all the correct degrees of freedom that you expect from the space-time calculation. So these formulae are written in terms of these twistor variables, right? And twistor space is some auxiliary complex projective space that's related non-locally to space-time. So if I'm meant to be computing something physical, the object I write down at the end of the day should have only space-time degrees of freedom in it, right? Or else I'm in trouble. Okay? And it should also capture all the aspects of the bulk Lagrangian. What I mean by this are things like factorization, 3-point functions, things like this. So if you, 3-point interactions maybe is the right word rather than functions.
So can we now try to find these KDIs in the ADS-DS case?
That's exactly what, yeah, that's exactly the idea.
Can I? So, before this, this second integral, there's no sense of what the external states are.
That's right. The external states are just these distributional delta functions. So the formula is kind of agnostic at that point about what the boundary conditions are.
This is where it's sort of
Exactly. That's where the boundary, and that's why my claim is that this is a good language for a first dash at trying to understand this, because it provides this clean split. You don't have to say anything about what the boundary conditions are until you want to obtain an answer in position or momentum space. It should match any available action-based calculations, and perhaps less obviously, but very importantly, it should have a smooth flat space limit. Right? And this is because this dude, this integral kernel, is meant to be capturing just the bulk part of the problem, right? And the action as a function of the curvature is smooth. It doesn't get singular when you send the cosmological constant to 0. It's only the boundary conditions that are jumping around. Right? So whatever you write down should be a smooth function of lambda, and in the lambda goes to 0 limit, it should reproduce the RSVW and the Kachazo-Skinner formulae, respectively. Okay? All right, so that's what we're shooting for. It turns out that in the Yang-Mills case, it's very easy, because the theory is conformally invariant. So recall our earlier discussions about the nature of Yang-Mills theory in 4 dimensions when there's a cosmological constant. So in the case of n equal 4 super Yang-Mills, because the theory is conformally invariant, this integral kernel with lambda not equal to 0 has to just be equal to the integral kernel with lambda equal to 0. In other words, it's just equal to the RSVW formula. Because the bulk action is conformally invariant. Bulk dynamics don't know anything about the fact that you've turned on a cosmological constant. It's only with the integration contour and the choice of external fields that you can differentiate between the fact that you're in de Sitter space, for instance, or Minkowski space. So it's easy to do here, right? Or at least easy to write down one of these integral kernels here. And this automatically obeys all of these properties. Okay.
But can you then confirm that you get the right amplitudes?
Good. So let me come back to that question. So now, when I consider gravity, life becomes more complicated. Okay, and it becomes more complicated because, of course, GR in 4 dimensions is not conformally invariant. The bulk dynamics know that you're on a different space-time, even if you forget about boundary conditions. Okay, so the answer needs to know about lambda somehow. And again, without going into any technical details, the way that you do that is with something called an infinity twister. For our purposes, this is just some skew-symmetric 4x4 array, so matrix, which has an inverse. And depends on lambda. Okay? Now, when I say introduce this, what I mean is that in the previous formula, in the Cauchy-Skinner formula, I had some determinants, some matrices. Okay? Now, in these matrices, in flat space, I had some spinor contractions, if you like, between the dotted and undotted components of a 4 momentum in flat space-time. So these would be, in traditional amplitudes lingo, these would be square brackets and angle brackets. And the idea is that basically, you just replace, everywhere you see a square bracket or an angle bracket in the Cauchy-Skinner formula, you just replace it with an infinity twister or its inverse. Okay? Okay. Now, if that was your guess, you would pass quite a few of the checks that are up here. You'd have a smooth flat space limit, because in the limit when lambda goes to 0, these infinity twistors go over smoothly to the usual spinor contractions. Okay. You would actually match available twister action calculations at 3 points. But, crucially, you wouldn't capture all the aspects of the bulk Lagrangian, and you would have the incorrect number of degrees of freedom. Okay? So it turns out that this isn't enough. You have to do more. You have to add a series of order lambda correction terms. And only if you add this series of order lambda correction terms do you get the correct number of degrees of freedom. Okay? So again, I can be more precise about this if people want to, but they may find it unilluminating. And so again, I'll just ask you to take my word for it that you can find this order, this series of correction terms that are polynomial in lambda. And the reason why you have to add them is that there's some gauge freedom on twistor space that doesn't exist on space-time. And if you don't add them, then this expression is not gauge invariant when you make this replacement. So you have some enhanced dependence in this formula that has no space-time analog. You have to get rid of it, yeah?
So what's the motivation for the smooth lambda goes to zero limit?
The fact that the action is a smooth function of the curvature.
So for example, the Maldacena-Pimentel formula that you wrote down, do those smoothly become?
No, of course not, because those aren't just the action. Those are after you've done the.
Okay.
So the way you would get the smooth limit there is you just take the residue of the pole in the energy, and then if you just truncate everything onto that residue, then that's a smooth. That has a smooth lambda goes to
So in
zero.
that case, that's talking about the transition amplitude, whereas here you're not talking about the transition.
That's right. That's right. That's right. I'm just like I said. The whole aim here is to split off this question of specifying external states and some contour integral from giving something that captures everything about the bulk evolution problem.
And does this sort of give you a sense of what kind of conditions have to be obeyed by the transition amplitude as lambda goes to zero? I mean, is there some simple?
Yeah. No. Well, I guess maybe I've said all I need to say. Now I can just make some general comments. So let me start with the bad news. So you can find, my point is that you can find something that passes all of these checks in both the gauge theory and the gravity cases, okay? So, bad news, I at least still don't have any good ideas for how to get the other part of the calculation into the game.
You mean the boundary conditions?
Yeah, exactly. For
Except at degree 1. I mean, degree 1, it's...
okay, so even then there's some subtleties. So there is a caveat to this. So in the MHV sector, for the Yang-Mills case, at least, I can reproduce all the MHV and MHV bar correlators that Maldacena and Pimentel wrote down. But the prescription one has to give for the contour integration is I don't want to say it's artificial, but basically you have some moduli integrals on twistor space. You always have to pick one of them to relax. So instead of picking a real contour that, I mean, Lionel made this comment earlier, instead of picking a real contour that runs from minus infinity to plus infinity, you just pick one of these moduli integrals that you've made some reality prescription for, and chop it off, and it goes from 0 to infinity now. Okay, and you always have to do this, and at least in the MHV case, it seems that you can be rather democratic. So using the vol SL2 or vol GL2 that you have, you can pick kind of any of the moduli integrals to relax in this way. So that's good news. For MHV bar, it seems maybe less democratic. Like maybe there's only 2 of the integrals that you can pick to relax. But that's not all. There's this pole and energy you have to find, and that relaxation procedure gives you the correct pole. But there's also some crap that depends on the energies of the individual particle states, if you like, that you're scattering. And that has to be there, or else the answer doesn't obey a certain Ward identity that's imposed by the de Sitter symmetries. And you can get, it's some overall factor. So in the MHV case, this is an aside. So in the MHV case, this would look something like K1 plus K2 minus K3, K1 minus K2 plus K3, minus K1 plus K2. Okay. And you'd think, okay, this is some overall factor, I don't really care about it, but actually it has to be there, or else the answer doesn't obey a certain Ward identity. And you can get this from the twistorial calculation by acting on the integral kernel with a certain product of differential operators. Okay? That is not, to me, a satisfactory explanation for where it should come from in twistor spaces.
So in the space-time calculation, is that just coming from sort of the bunch-Davies way of integrating it over the conformal time?
No, it isn't, actually.
It's not.
No, it's not. It's coming from using plane wave momentum eigenstates, but in this kind of 3+1 split for the spinor helicity formalism that's imposed on you by the de Sitter symmetries. So if you like, to get back to Louise's earlier comment, this factor will come out if you literally take the 3-point interaction from the Yang-Mills Lagrangian and plug plane waves into it. But they have to be plane waves adapted to the de Sitter isometries. So it's not just some overall factor that's there because you chose to normalize things appropriately. It really seems to be there.
Could you just say what this ward identity is? What's the symmetry that you're trying to?
I guess it's gauge invariance probably.
Just standard.
Yeah. But there's actually an even well, okay, I don't know if this is more powerful or not, but it's simpler to state perhaps. But there's also, and Lionel again helpfully brought this point
so
up.
in particular, you might mean is relevant in a collinear limit.
Yeah, absolutely. So yeah, if you had sort of well-separated operator insertions on your constant conformal time slice, perhaps you don't care about losing these overall factors, but
So this is sorry, we've been saying this, but this is a contact term back in the position space.
yeah. So the ward identity you need to satisfy the right-hand side will be some sort of contact term, and if you don't have these overall factors, you won't get it when you act with a gauge transformation. Another way of saying it is that bizarrely, well, not bizarrely, actually, it makes perfect sense. There's also new 3-point functions in momentum space when lambda is not equal to 0. So, for instance, in flat space-time, there's no all plus 3-point function, right? You always have to have at least one particle of different helicity. But as soon as you go to the case with non-vanishing cosmological constants, because you no longer have 4 momentum invariance, suddenly there are all plus and all minus 3-point functions. And this integral kernel doesn't seem to provide them, at least not in any obvious way. So you seem to be missing stuff. Now, I think I have an idea about why that's the case, but this isn't a proof, so somehow